Rodorico Giorgi es profesor asociado en el Departamento de Química de la Universidad de Florencia y su investigación está centrada en el desarrollo de nanopartículas. Ha participado en diversos proyectos, tanto nacionales como internacionales, en instituciones de México, Noruega, Suecia o Israel. También es autor de más de 100 publicaciones en el campo de las nanopartículas aplicadas a la conservación y restauración del patrimonio cultural. So, Rodorico, you have now 25 minutes for your talk and 5 minutes for any questions that may arise. Vais a tener, no va a poder estar con nosotros en la mesa redonda, así que vamos a dejar 5 minutos para cualquier pregunta que pueda surgir. Thank you very much, Rodorico. You can start now.
Thank you so much for your invitation, and sorry if I'm too excited and I started immediately. And my speech relies on de-acidification of paper, of cellulose-based artifacts, starting mainly from paper. And so let me go immediately to the point. The mechanical properties of paper comes from the glycosidic bonds. And so the integrity of cellulose molecules is the key point to have durability of this material, books, archive materials, drawing, and whatever. And you know that the main menace for this type of bond is water in presence of hydrogen ion as a catalyzer of acidic hydrolysis of cellulose that can lead up to the LO leveling off DP. So a polymerization degree below 400, that means that that paper crumble with handling, with simple handling. So it is pretty well known that hydrolysis can be inhibited by the application of alkaline materials to get a complete de-acidification. And this means neutralization reaction, basically based on hydroxide application. And the second step, fundamental step, is the formation of an alkaline reserve. We are pretty used to consider the two processes, hydrolysis and oxidation, few things a little disconnected and both very important to inhibit, to degrade paper, and for that the need to have methods to inhibit the two processes. And for inhibit oxidation, there are several methods that can be classified in with a general term of antioxidant. You probably well know the Bol-Langui autooxidation reaction scheme, where the loop where the cellulose go into can be stopped at several steps by using different materials, right, like a radical scavenger, peroxide decomposer, or metal deactivator, for example, the use of phytate. I want to show today, this morning, that the two processes are much more connected than expected. And so the pH control is the sensitive point to inhibit in a very good way the degradation of cellulose-based artifacts. We do that using alkaline earth hydroxide that we use dispersed in low polar solvents, low or medium polar solvent like alcohol. Why we use nanoparticles? Because using nanoparticles, we have a very fast neutralization reaction and a very quick carbonation of the hydroxide that change to carbonate. We obtain, thanks to alcohol, to low surface tension solvents, a good penetration and homogeneous distribution of particles. And we have also high compatibility with artworks because, you know, in the whole tradition of paper making process, starting from rags, calcium salts, calcium hydroxide was used for the treatment of rugs. And this means that we are confident that the presence of carbonate, calcium carbonate, but even magnesium carbonate can provide durability, long-term durability for the artifacts. On the other hand, the use of medium polar or low polar solvents is very important because we must have some compatibility with inks, dyes, or sizing. And using nanoparticles is possible to work in a non-aqueous environment. We use calcium hydroxide or magnesium hydroxide, which are the compounds, especially magnesium hydroxide, which are the intermediates of most of the acidification methods used also at the industrial level, for example, in the mass deacidification processes. So the properties of magnesium hydroxide, calcium hydroxide are pretty well known, and we know exactly what we'll have when we have carbonate within the fibers. Here we have some pictures showing particles that we obtained in the research of the last 20 years, starting from different methods: homogeneous phase precipitation, hydrothermal treatment of slake and lime, or alkothermal synthesis starting from metal calcium. Using different methods, we can tune the average size, the size distribution, and we can better address the specific needs we have working not only on paper, but also, for example, for textiles or wood. And as you can see, this research dated back to the beginning of the century. 2002 was the first work. And also for magnesium hydroxide, we obtain particles with the right size, with the right size distribution, with different approach. The first point, very important, is the kinetics of the process of calcium carbonate formation. In this case, you can see some infrared spectra, where you can see that with time, in a few weeks, we have a significant increase of calcium carbonate signal, 875 wave number. And you can see that just after a few hours or couple of days, no more than a couple of days, the signal coming from hydroxide completely disappear. So fast neutralization reaction and very quick transformation of hydroxide to carbonate. Here we have some data about the mechanical resistance to the tensile strength of samples treated, for example, with alkaline nanoparticles, such as, for example, in this case, magnesium hydroxide. It's interesting to see that paper protected with the application of particles, the application preserved the mechanical properties of paper. Here we have different samples with different tensile strength at the starting point, and you can appreciate the differences after artificial aging. You can see that we have a drop of mechanical resistance for the samples not treated at all. And you can see the beneficial of the application of method. MMC stands for methoxy magnesium carbonate, a very well-known deacidifying agents. And it is compared with magnesium hydroxide. Remember that MMC is the precursor of magnesium hydroxide in some of the deacidification methods used also at industrial level. And you can see that the mechanical properties are preserved. Now I want to go into detail to my opinion, the really most important point, that is the question, deacidification or pH control, which is the final pH we must achieve thanks to a deacidification process. Because deacidification is not so specific. What does it mean? pH 7, 8, 9, 11, or pH control. It is possible to predict the final pH of the application, which is the ideal pH condition to preserve artworks. And we focus this question working on the issue of inhibition of cellulose corrosion due to iron ions activity. All of you well know that iron gold ink is a really nice ink, really beautiful and very stable when prepared according to specific recipes. But you know that in the past, a lot of recipes foreseen a significantly higher amount of iron, more than necessary. The work by Jan Nivel, beginning of 90s, was really important because working on more than 100 different recipes, you realize that most of them, the majority of them, go beyond the right ratio between the amount of iron salt and gold. This means that we have a lot of free iron ions, which unfortunately, under normal condition and in acidic environment, leads to formation of peroxide. And the presence of peroxide in situ produce, due to the well-known Fenton reaction, the presence of hydroxyl radicals. The presence of radicals create very strong oxidation of cellulose, and we have the starting of the process that is an autocatalytic process, because we go into this loop and we cannot escape unless we are able to inhibit, to stop some of this reaction. And for this purpose, as I already told you, antioxidants are applied. Antioxidant in the sense that we apply something that can inhibit this process that leads to oxidation. And so we have the possible use of real antioxidant, like, for example, radical scavengers or peroxide decomposers, which are halogenated compounds of ammonium salts. And the well-known phytate, that is a metal deactivator, a way to remove free iron ions, which is the starting point of the process. But the catalytic activity of metals strictly depends on pH. And this paper by Matthias Strilic and Jana Kolar is very, very important because it focuses for the first time the importance of pH in the inhibition of this catalytic activity. For example, it is well known that in acidic medium we have the activation of this Fenton reaction, but we also have such activity if we go at higher pH, higher than 8.5 in the case of iron, and even less in the case of copper, that sometimes more than expected is present as a contaminant of iron gold ink. So looking at these two experimental data provided by Strilic and Kolar, we realize that neutrality are the best condition in order to inhibit OH radical production. And so for that reason, we make this type of experiments. We prepare a set of inks with different composition, starting with a classical iron gold ink recipe, which contain a high amount of iron. We are in large excess of iron. When we use gold and nuts in the weight ratio 1:1, that is the ratio that we usually found in the recipe, in the old recipes, in this condition, looking at the the number of moles involved in the process, we have a very large excess of iron. And this means that we have an ink that is much aggressive. If we modify this weight ratio, we can get iron gold ink, which are less aggressive. And we also prepare a set of inks where we have a different ratio between iron and copper, because in many cases we have the presence of copper, and in some cases this is in very relevant amounts. Then we apply this type of inks on Whatman paper that is pure cellulose, no sizing. This means that the ink is even more aggressive for cellulose, because cellulose are naked and no protection in any way. And then we compare different treatment, which is the effect of simple immersion into water that implies the removal of the excess of iron that is obviously soluble in such condition, and the comparison of a treatment with alkaline nanoparticles and with a classic antioxidant, for example, tetrabutylammonium bromide in water. Then we apply some aging method, classic hydrothermal accelerated aging, high temperature, high relative humidity, and this is what we observe. It is impressive because only 48 hours are enough to completely change the mechanical properties of cellulose, to have discoloration of inks, but above all, paper has lost completely the mechanical properties, the tensile, the resistance to tensile strength and elasticity. Exactly the same sample that was treated with nanoparticles to reach pH around neutrality, exactly the same inks did not produce any of these effects, preserving good elasticity of paper, good mechanical resistance, and any color change. If we measure, thanks to measurements of polymerization degree and evaluating the percentage of broken bonds, as we usually do for a kinetics study of the degradation process, we can see the benefit we have thanks to the application of antioxidants. We see that the curve has a lower slope, significant reduction. We can see, comparing these graphs, that obviously we have also some benefit simply by washing the paper. But this is because we remove the iron excess. And for that, paper is more resistant under this condition. But obviously, the removal of iron as an excess, we know that is detrimental, but this is still part of the original document. If we look at the effects of a deacidification, I say deacidification, but better to say pH modification to get pH around neutrality between 7 and 8, we can see that the same behavior we obtain using antioxidant is obtained simply by modifying the pH. You can see here that the two curves in the larger graph refer to the application of, in this case, magnesium hydroxide, compared with the bookkeeper method. You know, bookkeeper use magnesium oxide, which turns into magnesium hydroxide. So at the end, the neutralizing agent is the same. And you can see, you can appreciate that we have the same benefit we have applying antioxidants. And that's why we firmly believe that pH control is the first step in a good conservation intervention to preserve paper from further degradation. About nanoparticles application, today such knowledge has produced products that are available on the markets. And as CSGI, that is the National Consortium in Nanoscience, which is headed by University of Florence, we create this trademark to protect the intellectual properties of this achievement. And this is also because European Commission that funded most of our research promote all the steps necessary to get the end user to arrive to fill the gap that we usually have from the research lab and the practical use of end users. And today, this concept has produced something that is available on the market. Formulation that is in alcohol, ethyl alcohol, propylic alcohol. And here we have very quickly described the procedure we suggest, we recommend. Obviously, it is very important to check first the compatibility with ink, then measure the pH. The application of nanoparticles can be done by applying it by brushing or by spraying, depending on different conditions. Then, at room temperature, with relative humidity at least 60%, we have the carbonation process, which takes, as I told you, a few weeks. And then we check the final pH. The application of nanoparticles allows repeating the process step by step to get the final pH. And this is something completely different approach with respect to other methods where the control of the final pH is not so easy. The ideal conditions are around neutrality, but we have verified in several different case studies that depending on ink's composition, pH can reach also pH 9 without any serious side effects. Here we have some examples of applications. I want to start with this one because this is a very precious collection of drawings, painted drawings, glue on paper. And as you can see, paper strongly oxidized and very, very damaged with pH extremely low. This work was done at the Italian Institute for Conservation in Florence, Opificio delle Pietre Dure. And here the protocol was defined and applied, even for paper so degraded and oxidized to reach a pH that was acceptable for the conservation of the original drawings on top of it. And then we use these methods also for the deacidification of Codice Fiorentino, which is conserved at the Laurentiana Library in Florence. This comes from colonial time in Mexico, in Tenochtitlan, and was realized by native people with friars living in Tenochtitlan. Iron gold ink was used, and we had acidic condition of paper and also, unfortunately, some ink corrosion issues. But we also have roughly 3,000 drawings made of dyes and colorants coming from the painting tradition in Mesoamerica. So it was very important to work with something compatible with these materials, which are really sensitive also to pH variation and obviously to the effect of solvents. In order to define the right setup for working on that, we start working on paper with similar composition, the same grammage, the same pH condition, in order to define the best procedure and the right amount to apply in order to have a good mild variation of pH to reach neutrality. This was the approach we followed. that was at the end successful, and the codex, the Florentine Codex, was deacidified. Just the last slide, just to say that these particles can be also dispersed in low polar solvents, for example, cyclohexane. This is pretty relevant when we talk about graphic materials, contemporary graphic materials, like, for example, biro, ballpoint pen, technical pen, felt tip pen. In this case, we have formulations that are fairly stable, kinetically stable. You can see here the sedimentation rate of these systems, but nanoparticles can be dispersed for an acceptable time range for the application, for example, using the spraying technique. Working with cyclohexane prevent from the risk we might have working on some specific inks with alcohol. For example, in this case, we have that black ink with a trademark Pilot is not sensitive to propanol, 1-propanol or 2-propanol, and this means that we can use the original formulation. But when we have biro ballpoint pen like big one, in that case, alcohol could be used by dropping, could be not compatible. In the same condition, cyclohexane is perfectly inert. Obviously, the application technique is very important. It's not possible to deacify using propanol, using the technique of brushing, but in specific condition, we can also use alcohol by nebulization, even on inks that are more sensitive to the solvent. I think I perfectly respected the time. I hope so. I think so. And so, obviously, what I presented is the result of a teamwork. Piero Baglioni is our director, and here we have a list of projects we are involved in, European projects that has funded our research. And here you can see also my email address. I will be happy to answer your questions that may come out in the next days. And so I thank you all for your kind attention.
Thank you so much, Rodorico, for sharing your impressive research. It's really incredible that we can get the same benefits using antioxidants versus simply neutralizing the pH. We really appreciate that you took the time to be here today, and we have so many questions for you. I'll try my best to share that. We have a question that says, how did you measure the mechanical resistance? Which equipment? And were the tests, and if were the tests destructive?
Oh, yeah.
And
I show in the slide, we use a classic dynamometer used in textile industry to check the mechanical resistance of a single fiber. In this case, we use a protocol that is largely used on that area, and that we modify a little because obviously the strength involved in the process is lower. Usually lower than the ones that they use. Anyway, this is a classic procedure, pretty largely used, and there is a dynamometer, and obviously we work on the technique is destructive, obviously, so we cannot check the benefit of the treatment on the real artworks. What we can do is working on mock-ups, and very often on old materials that have similar characteristics, like in the example I did about Florentine Codex. It's very precious when we have materials that mimic the characteristics of the original artwork. And for our research, this is a very important because we can make measurements, we can do tests that we cannot do on real objects. In a few cases, for example, a collection from the Correr Museum in Venice, quite often there are pieces of paper that are without any inks, without any information, and that cannot be reassembled in the original one. And this type of samples are very precious for our investigations. I hope to have answered your question.
Yes. Well, we have another question also about personal protection to manipulate nanoparticles or to use nanoparticles.
Yeah, sure. Yeah, you mean the exposure scenarios. So we don't have particles free. We only have particles in suspension. And this means that the exposure scenario is completely different. So any risk to inhalate nanoparticles. If you work with a nebulization method, obviously you must have the usual care you have when you use that type of technique, because it is clear that in that case you produce droplets. And for example, for the deacidification of Florentine Codex, we did this on inside the chamber with a control from outside and using a nebulizer. But there is no specific risk about the toxicity of particles, because particles are dispersed in a liquid medium. You must take care in case you have you use the nebulization technique. We recommend a protection with gloves, but this is because it is a pretty alkaline materials. We are not working in water, so the pH is not so aggressive, but obviously you must have this attention. Anything else?
Yes, well, we have one of our speakers, Jasna Malesic, that would want to or would like to ask her questions in person since she's connected. So Jasna, if you could turn on your camera and your mic.
I am. Do you see me and hear me?
Yeah.
Yes, we can hear you.
So thank you very much, Rodorico, for your presentation. I would just like to highlight a little bit and ask some questions because you didn't actually tell us everything about nano calcium hydroxide. The first thing is that actually I tried your nanoparticles dispersion by myself. I can agree that calcium hydroxide was used for the rag papers, and also I don't think it causes any troubles with calcium with rag papers. But then usually we don't have only rag papers, we have some application of some ink and some pigments, and we know that mostly we have machine-made paper containing lignin. And when I tried to spray your particles dispersion on the lignin-containing samples, I ended up with yellow dots, because we know that it takes quite some time to change from the calcium hydroxide under the room conditions. It takes quite some time to change to calcium carbonate. And this time is really problematic, because you can end up with discoloration of the paper artifacts. And moreover, you didn't show that, for example, in case of iron gold ink, we know that iron gold ink complex is not stable at such a high pH values. And also, that's not even magnesium carbonate was discouraged to be used on iron gold ink documents, because it induces discoloration, because it's just the complex is destroyed. And there is another thing. We know that iron gold inks can have up to the same molar ratio of copper ions, and copper ions increase their catalytical activity with increasing pH values. So I would really like to discourage the use of nanoparticles for deacidification. I mean, calcium hydroxide nanoparticles for deacidification, either of lignin-containing paper, either with any kind of paper that has some pH-sensitive material on it. And really, this is my point, and I would like to see your explanation why this is not true.
Obviously, I disagree. The point is that if you consider all the other alternatives, the other deacidification method, you would have exactly the same issues, because we are talking about the same things. Most of the acidification methods, they can mention Booksaver, Bookkeeper, Weight-O, whatever, use magnesium hydroxide. If you use aqueous method, you have a huge number of problems due to pH. It is pretty obvious that in 30 minutes, I cannot consider all the cases. I focus my presentation on classic iron gold ink. Obviously, if we talk about iron gold ink, it is pretty obvious that we talk in the most of cases about paper made from rags, because obviously machine paper is from the land of 19th century, and in that case, the use of iron gold ink is much less common than the ones we had for centuries. I also highlighted, to my opinion, the differences between copper and iron. It is pretty clear that if we have ink containing copper, pH 9 cannot be reached, but for sure, around neutrality, the catalytic activity is very low, and you know very, very well. So I may agree with you, but first, we must consider the alternatives we have. Secondly, it is obvious that we have a huge amount of different substrates to work with, and what I'm presented is the general concept. The chemistry is always the same: calcium hydroxide or magnesium hydroxide. At this moment, nano-restore paper is calcium hydroxide. We prefer calcium hydroxide for several reasons. But why we also investigated magnesium hydroxide? Because the intermediate in the almost all the deacidification method today available at industrial level, I mentioned some, I may have the Battel method and whatever, use magnesium hydroxide. And so we want just to see if the direct application of magnesium hydroxide provide similar results. And this is obviously the case, because the chemistry is very, very simple, anything different. About the carbonation reaction, it is clear, and I mentioned which are the ideal conditions in a room environment. If we have a very low relative humidity, the carbonation reaction is slower. And this means that in the application procedure, we must take into account which is the relative humidity in the environment. If we have 60% relative humidity, that are the comfort condition in a lab, the carbonation reaction is very, very fast. So the hydroxide disappears completely. We have carbonate, and we don't work in an aqueous environment. We work on alcohol. This means that pH concept must be revised completely. pH concept comes from water, aqueous solution. If we have alcohol system, it's a completely different kinetics. And basically, I agree with you. If we have lignin, we might have stains if we are not in the proper condition, because obviously in that case, you might have this problem. But I can show you, I can demonstrate that, well, the same chemicals can be used in different conditions, and 90% of the cases, you don't have this problem with different type of paper working on the same paper, but with different conditions. So one thing is the chemistry. that underpin the process. Then we have the application method. And we have to consider several factors. And in that sense, I totally agree. So it is clear that I could make this presentation again for 20 different types of paper, and I would say, by chemical point of view, the same thing. But for sure, we should revise the protocol, because the environmental conditions that in the past were never considered too much are very important, for example, for controlling the process.
Thank you,
Okay.
Rodorico. I would just like to state that we as a chemist, I'm also conservator. That's why I have some feeling what means damage to the paper artifacts, and I'm always aware of that. And that's why
I'm so
that
sorry, Jasna.
Yeah.
Jasna and Rodorico, this is a very interesting discussion, but I'm so sorry to say we don't have time. It's already we're already 15 minutes behind the schedule, and well, we'll discuss further in the panel discussion, even though Rodorico is not there.
Thank you.
So thank you so much, Rodorico.
Welcome. Thank you.